All right, so with this chapter, we're going to start to look at some of the math of chemistry and how we can kind of keep track of how much of a substance we have, because we're going to see that the mass isn't going to be allow us to kind of relate one substance to another, just because we're going to see each of these pieces, whether it's an atom or a molecule, is going to weigh a different amount. So first, we want to think about what's known as formula mass, and essentially what this is, sometimes also known as molecular mass. They're synonymous terms. What this is just essentially looking at the chemical formula, then using the periodic table to sort of keep track of what elements we have, how many of each of those elements do we have, and then kind of just adding up all of those different pieces. So with the examples on the right here, the top one is chloroform. So 1 carbon, 1 hydrogen, 3 chlorine. You can see the formula right here. The bottom one being aspirin, so C9H8O4. And when we're looking at a calculation like this, when we're trying to get the molecular mass or the formula mass, or we'll see later on there's a synonymous, or not a synonymous term, but a very similar concept known as the molar mass. It's just sort of the scale we're looking at that's going to be different. That'll change the unit, but the math process itself is still going to be the same. What I would recommend you doing when you're doing a calculation like this is for each element in that substance, so carbon, hydrogen, and chlorine for the first one, carbon, hydrogen, and oxygen for the second one, just have a separate line so we can keep track of how many atoms of each of those elements do we have. And then the average atomic mass, this is just coming from the periodic table. So for carbon 12.01 or hydrogen 1.008, chlorine 35.45. So depending on which periodic table you're using, the textbook versus the one that I gave you in the reference sheet, I think is a little bit different. I think yours would say 12.011, or I think there's an extra digit with chlorine as well, 15.99 with oxygen. But regardless, the process is still going to be the same, where we're just keeping track of how many of those atoms we have, and then essentially just multiplying it by how much each of those weigh, and then just adding up all of those pieces. And the reason I would recommend kind of a format like this where each element has its own line is because then we can get the mass of that element individually. We can add it up and get the molecular mass or the formula mass, so we can get the mass of the entire molecule. But by doing this, we're going to see in the second half of this chapter, there's going to be a percent composition calculation. And by setting it up like this, we'll have all of the pieces we can need there. But with the formula mass or the molecular mass, what we're going to see is the unit for that is going to be AMU, so atomic mass unit. And when we're thinking about the formula mass or the molecular mass, we're essentially just thinking about if we had a single molecule of this substance, how much would it weigh? But what we're going to be doing when we're working with real samples is have a whole bunch of those molecules together. So we're going to have a slightly different unit that we'll wind up using instead of molecular mass. But with these ones, if you want to practice, we've got ibuprofen on the top, so C13H18O2. And then at the bottom, we've got another pain reliever in acetaminophen, so CH89NO2. And again, for each of these calculations, I'd recommend just having a different line for each of those elements, multiply however many of them we have by the mass from the periodic table, and then just add up all of those pieces. So with the ibuprofen at the top, we've got 13 carbons, each of them weigh just over 12, 18 hydrogens, each of them are just over 1, and then we've got 2 oxygens that are both 16. So we can get the mass of each of those elements individually, and then just add them all up to get the molar mass, or the molecular mass, I should say, which we'll have in the unit AMU. And then with acetaminophen, would be kind of the same idea. We'll have 8 of those carbons that are 12.01 each. We'll have 9 hydrogens that are 1.008 each, 2 oxygens, 16 each, but then we would also just have an additional nitrogen, so 14.01 or 14.007, depending on what periodic table you're using. But adding all that up, we'll get 151.16 AMU. And then with the ionic compounds here, so if we go back for a second, these were all covalent. We just had nonmetals, so carbon, hydrogen, chlorine, oxygen, nitrogen, whatever it may be. But they're going to share those electrons. So we can actually have the covalent bonds holding those atoms together. With the ionic ones, we actually have a transfer of electrons. So if we think about this aluminum here, it's really not an aluminum atom. Each of those would be the aluminum ion, so with a +3 charge. They lost 3 electrons. But when we're looking at these ionic compounds, we can go about the calculation the exact same way. Because even though the mass on the periodic table is for the neutral atom, remember that the electrons, so again, aluminum is going to be 3+. Remember that the electrons are going to be so small in comparison to the protons or the neutrons that we can essentially just ignore them. So it doesn't matter if aluminum is neutral or aluminum is 3+. We can still use that same average atomic mass from the periodic table. And then with these ionic compounds, when we're thinking about a neutral formula, it matters even less because the electrons that the cation, so in this case the aluminum, the electrons that cation are going to lose are going to be the same electrons that the anion would gain. So it would still have all of those electrons present. But again, they're so minimal in comparison to the protons and the neutrons that if we were looking at just the mass of an aluminum ion, we could still just consider it the same as that atom. But with these ones, the big thing to remember is that when we've got something in parentheses, like the phosphate PO4 on the bottom, or the sulfate ion SO4 on the top, whatever the number is on the outside of that parenthesis, we distribute to everything within it. So that's why for this first one here, we of course have 2 aluminum, but then we've got SO4 in parentheses with the 3 on the outside. So we're really distributing that to the sulfur and the oxygen. So we've got 3 sulfurs, we've got 12 oxygen, because we've got 3 of these sulfate ions. Similarly with calcium phosphate, we'd have 3 calcium, but then we'd have 2 of these phosphate ions, so we'd have 2 phosphorus, we'd have 8 oxygens, and if we added up all of those different atoms, we'd wind up with 310.18 as our molecular mass in atomic mass units. But we're never going to be working with just a single atom of a sample. We're always going to have a much larger collection of atoms or molecules, even depending on what the substance is. But because these molecules are all going to weigh different, we can't just use the mass to directly relate one with the other. So if we look at the image here, in each of these samples, we've got just elemental zinc or carbon, magnesium, copper, sulfur, silicon, lead, tin. And you can see the mass that we have in each of these samples. But with all of these samples, this is known as 1 mole of that sample, because in each case, we're going to have 6.022 times 10 to the 23rd atoms of whatever that element is. So we've got the same number of atoms in each of these samples, but because each of these atoms weighs a different amount, that's why we've got over 200 grams of lead versus only 12 grams of carbon. A carbon atom is much, much smaller than a lead atom. So we just have less mass of it, even though we've got the same number of those atoms. And with this, in order to relate these substances, in order to keep track of how many atoms or molecules we have, we've got the term known as the mole. And that's probably the most important unit in chemistry, because a mole allows us to keep track of how many atoms, how many molecules we have. So we can actually use the mole when we're thinking about a chemical relationship to relate the amount of one substance to another. So if you think about a chemical equation showing a reaction, we've got the numbers in front of those different substances. That doesn't tell us the mass. That tells us how many of those molecules or atoms we're going to need. So that's telling us how many moles of those substances we need in ratio or in relationship with one another. And then with it, this number 6.022 times 10 to the 23rd, we can think of as a similar concept to the dozen. It's just whereas dozen represents 12, 1 mole of anything is going to be this many of whatever that thing is. So it could be atoms of zinc. If we had a mole of bagels, it would be this many bagels, 6.022 times 10 to the 23rd. But the mole is just simply representing some number, and that's known as Avogadro's number specifically. So when we're working with the samples, again, we're never going to have a single atom or a single molecule. So rather than using the formula mass in AMUs, what we're going to do is simply change that unit to grams per mole. And what that's going to represent is how many grams of that substance would we have if we had 1 mole of that substance. So if we had 6.022 times 10 to the 23rd of whatever that is. So if you look at the few examples here, carbon, hydrogen, oxygen, sodium, chlorine, we can see the mass of these from the periodic table in atomic mass units. But then with molar mass, grams per mole, so we had 6.022 times 10 to the 23rd. It's still that same number. We just have it on a different scale, so we have that different unit there. And what this molar mass, what this grams per mole is going to allow us to do is to convert between the mass of a substance, which is something we can easily get from the balance in a lab, to the number of moles of that substance, which then allows us to relate it to different substances. Excuse me. So again, looking at the image here, we've got the samples of octanol, so C8H17OH, mercury 2 iodide, HGI2, methanol, CH3OH, and then sulfur, S8. And in each case, we've got 1 mole of this substance. So we've got 1 mole of each of these substances. We've got 6.02 times 10 to the 23rd molecules of each of these substances. But because a methanol molecule is much smaller than the rest, we've only got a little bit of that sample. And then it's kind of hard to tell with the mercury compound, but because that mercury 2 iodide is a much more massive molecule, we've got a lot more mass of that substance than we do the other ones. I think if we actually added it up, we'd have more of the mercury 2 iodide in terms of grams than we would the other 3 combined. But in each of these samples, we still have the same number of molecules total, 6.022 times 10 to the 23rd. And then just to put the number of these molecules or atoms into perspective, if we had a droplet of water, so you can see here just a regular droplet, of course the exact size of it's going to vary depending on the droplet itself, but a rough estimate of a water droplet would be 0.03 grams, so very, very small mass to begin with. But to put into perspective how small these molecules are, if we took this droplet of water and then split it evenly amongst everybody on the planet, so at the time the textbook said roughly 7 billion, I think we're now up above 8 billion, but if we split this water droplet evenly amongst everybody on the planet, of course the actual mass that everybody would get would be undetectable, but the number of molecules in each of those different samples would be over 100 billion. So again, these molecules are so tiny. Avogadro's number is so huge that we use the concept of a mole, so we can actually make sense of and understand kind of how much of this sample we have without having to use like 10 to the 23rd or something like that in our calculation. So it just simplifies it slightly. And like I said, we're going to be able to use that to convert between grams and moles of these different samples just by using the molar mass. And if we think about a question like this, so the USDA estimate for dietary potassium is 4.7 grams. We want to figure out how many moles of potassium you would need on a daily basis. What we're going to be using is just the molar mass. And then because the molar mass itself is in grams per mole, we can use that as a conversion factor. Because grams per mole, in this case 39.10 for potassium, just because it's that single element, so just K by itself. But what this is saying is there's 39.10 grams per mole. So for every 1 mole, that's equal to 39.10. So we're going to be able to set up our dimensional analysis just by focusing on the units, essentially. And the reason this works is because just like when we were converting length or mass units, the numerator and the denominator of those parentheses in our dimensional analysis were equal. So we were just essentially multiplying by 1. We were changing the unit by keeping the quantity the same. We're going to do the same here. So we're going to have 0.4 grams, or 4.7 grams, excuse me, of potassium to begin with. We're going to figure out how many moles of potassium that is, but it's going to be the same number. It's going to be the same quantity overall. We're just expressing it in a different unit. But with these ones, we can just start with the value we know, 4.7 grams. And then with the molar mass, we just have to kind of organize that so that the proper units cancel. So since grams is what we're starting with, grams is what we need to cancel, we need to put grams on the bottom, which means mole of potassium has to go on top. And then like I was saying, this parenthesis has to be equal to itself in terms of the numerator versus denominator. So if we had 1 mole of potassium, that's going to be equal to 39.10 grams. That's why we plug in the value there on the bottom. And then with this actually going through it, we've got 2 sig figs in our initial value, so we should have 2 sig figs in our final value. And then if you want to, you can practice with a very similar calculation on the bottom here, but with beryllium, which is a light metal used to fabricate transparent X-ray windows for medical imaging instruments. And we want to figure out how many moles of beryllium would be present in a thin foil window that weighs 3.24 grams. Again, it's going to be that same idea. We can use the molar mass. We can set it up in the parenthesis in order to convert, cancel out grams, and we'll be left with moles of that sample. But in this case, since beryllium, the beryllium atom is much smaller than the potassium atom, so if we had 1 mole of beryllium, now we would only have just over 9 grams of beryllium. So when we do our dimensional analysis, still grams is going to cancel. We're left with moles of beryllium. We had 3 sig figs to start, so we should just have 3 sig figs in the end. So we're going to wind up with 0.360 moles of beryllium there. And then with both of these, with all of these calculations we're going to see, just think about if the value makes sense in terms of essentially just bigger or smaller than 1. Because with this one, 3.24 grams, but 1 mole of beryllium is 9 grams. So we've got less than 1 mole. We should wind up with a mole value lower than 1. And then the same thing with the top one here, potassium, we only had 4.7 grams. 1 full mole of it is worth 39.10. So we should again wind up with a value smaller than 1. If you wind up with a value much larger than 1, you most likely just multiplied when you should have divided. So we can always use that as just kind of a rough estimate to see if we're on the right track. And then with the next one here, kind of just going in the opposite direction in terms of what we're converting. With those previous ones, we had the number of grams. We wanted to figure out how many moles. In this case, we know there's 9.2 times 10 to the negative 4th moles of argon in a liter of gas. We want to figure out what mass of argon would be present in that sample. But again, we can use the molar mass, and since we're still just looking at an element, it'll still just be the value directly from the periodic table for that element. So we can just find argon, which is going to be just under 40 in this case. But now when we set this one up, we're starting with moles of argon. So in this case, we want moles of argon on the bottom of our parenthesis. So we put the gram value on top. And again, units are just going to cancel as we need to. Now we're just left with the mass of this sample. And just like the previous one, we can think about if that number makes sense. Because with 9.2 times 10 to the negative 4th moles, we've got a lot less moles than 1. So we should wind up with a much smaller value than 39.95. And 0.037 definitely fits that bill. So it makes sense that that's our answer. And again, looking at sig figs, 2 sig figs and 9.2 should have 2 sig figs in our final answer. And that's what we have with 0.037. And then with the next one, mole of, or how many what is the mass of 2.561 moles of gold? It's going to be that same idea. We'll plug in 2.561 moles of gold. It's just in this case, instead of the molar mass of argon, we would just use the molar mass of gold, which is going to be almost 197. So if we've got 2.561 moles, each of them weighs about 200. So 200 times roughly 2.5. We should wind up with something around 500. So when we get 504.4 grams of gold, that's a reasonable answer there. And then with this one, if you want to practice with any of these, just make sure, as always, you pause the video. Just give yourself a chance, because I'm just going to kind of go through a lot of these examples. But with this one, now we're looking at copper, which is commonly used to fabricate electrical wire. And that's why oftentimes construction sites tend to get copper wiring stolen from them. They use that in the building. And copper is a slightly more valuable metal than quite a few others, so you can sometimes sell it for the scrap. But we want to determine if we had 5 grams of copper, 5.00 grams of copper, how many copper atoms would actually be in that sample. And in this case, we still need to use the molar mass, but we're going to go one step further. We can use this value and then the molar mass of copper to figure out how many moles we would actually have of 5 grams. And then using that mole value and using the relationship between mole and Avogadro's number, we can convert to the actual number of atoms there. So if we look at this one here, we've got copper. We can get the molar mass just from the periodic table. So if we did 5 divided by 63.55, this would give us however many moles of copper we had. And then since 1 mole just represents 6.022 times 10 to the 23rd, we can just take the mole value for copper and multiply it by Avogadro's number just to get however many atoms we would actually have there. And again, with this one, we can think about if this answer makes sense at all. We've got 5 grams of copper, much less than 1 mole. So we should have less than 1 Avogadro's number worth of copper atoms. And 4.74 times 10 to the 22nd is less than Avogadro's number. So that makes sense. So if you want to practice at this one, again, same kind of idea. A prospector panning for gold in a river collects 15.00 grams of pure gold. How many atoms of gold are in this quantity? So again, we need to use the molar mass to convert to moles, and then we can use Avogadro's number to actually determine how many atoms we would have. And in this case, Avogadro, or the molar mass of gold, just under 197. So if we divide these two together, we'll get the actual number of moles of gold we have in this sample. And since we've got much less than 1 mole of gold, we should wind up with a pretty small number. But then we can take that mole value and just multiply it by Avogadro's number. Because if we look, grams are going to cancel, moles are going to cancel. So we'll just be left with atoms of gold there. So again, in this case, we're just going one step further and thinking about what a mole actually represents. So just like if we had 2 dozen of something, we would have 2 times 12, we'd have 24. It's the same idea here. If we had 2 moles, we'd have 2 times 6.022 times 10 to the 23rd. It's just in this case, we're figuring out how many moles we have to begin with, and then we're multiplying it by Avogadro's number. Right. And with the previous ones, we had just been thinking about elements. So we could just think about potassium or gold or whatever the element was, and just get the mass from the periodic table for the molar mass. For these next ones, now we're going to be looking at compounds. So we've got to consider the entire formula. So for a question like this, our body synthesizes proteins from amino acids. One of these amino acids is glycine, which has the molecular formula given. How many moles of glycine molecules are contained in 28.35 grams? So in this case, we're going grams to moles, but we've actually got to do a little bit of math to get the molar mass. We've got to add up 2 of those carbons. We've got to add up 5 of the hydrogens, 2 oxygens, and a nitrogen. And when we do that, we're going to get 75.07 grams per mole. So if we had 1 mole, if we had 6.022 times 10 to the 23rd molecules of glycine, we'd have just over 75 grams. And for this one, we're told we have 28 grams. So we've got a lot less than 1 mole. We should wind up with a value smaller than 1. So when we do our dimensional analysis, at this point, it's still going to work exactly the same as the previous ones. We had our mass of our sample. We have the molar mass. We can just cancel out those units. And now we're just left with moles. And we'll get 0.378. And with this one, it comes from the textbook. I would actually disagree with this. Because if you look, we've got 4 sig figs in our mass value to start. We should have 4 sig figs in our mole value in the end. But this is only reporting 3, so there should be 1 extra digit. So it should be 0.378, whatever. Or it should be 0.377 something if we round it up to get to the 8 there. But either way, we know we're in the right ballpark just because we're getting a value smaller than 1, which is what we should if we only had 28 grams, and that substance has a molar mass of 75. So then with the next one, sucrose, just going to be a type of sugar, and it's got the formula C12H22O11. We've got 25 grams of sucrose. We want to figure out how many moles of sucrose we're going to have. So again, the first thing we've got to do is figure out what the molar mass is. We've got to add up 12 carbons with 22 hydrogens with 11 oxygens. And when we do that, we're going to get a molar mass of 342.297 grams per mole. But since we're starting with grams, we're going to flip that molar mass in terms of our conversion factor. We're going to put the 342 grams on the bottom, 1 mole on top, so that we can cancel grams, just be left with moles. And we're going to see in this case that gives us 0.073 moles of sucrose. So with these types of calculations, hopefully you're kind of seeing that they're always going to be essentially the same process. We'll see in some cases we've got extra steps, but we can always kind of focus on these units. We can use the molar mass to go from grams to moles or back and forth. And then to get the actual number of atoms or numbers of molecules, we can use Avogadro's number in order to make that conversion from moles to the actual number. So for this one, vitamin C is a covalent compound with the formula C6H8O6. So it's also just known as ascorbic acid. The recommended daily dietary allowance of vitamin C for children 4 to 8 years old is 1.42 times 10 to the negative fourth. We want to figure out what the allowance would be in grams. And again, the first thing we should always do here, if we're not given it directly in the question, is figure out what the molar mass is. So in this case, we've got to add up those 6 carbons with the 6 oxygens with the 8 hydrogens. And when we do that, we're going to get a molar mass of 176.124 grams per mole. So again, just think about your answer, or think about your starting value. We have a much smaller sample than 1 mole's worth. So we should wind up with an answer that's much less than 176, because we don't even have 1 full mole of it. But again, when we're plugging it in, just like we saw with the element, we can focus on the units. We're starting with moles. That's how much, that's the sample we know. The molar mass is always going to be our conversion factor. So we can just set that up so that the units cancel. In this case, mole on the bottom, which means we've got the gram value on top. And when we multiply that out, we get 0.0250 grams of vitamin C. And then in this case, it does match up 3 sig figs to start, 3 sig figs in our final answer. So again, just focusing on those units, using the molar mass however we need to in order to cancel the proper units. So with the next one, hydrazine, same idea. We've got 0.443 moles of hydrazine. We can get the molar mass, which is going to be 2 nitrogens. So 14.007 times 2, 4 hydrogens times 1.008, and then add those 2 together to get the molar mass of 32.046 grams. We can set it up so that moles cancel. And in this case, we're going to get 14.2 grams. And again, that makes sense because we've got less than 1 mole. So we should have a mass value smaller than the molar mass. We should have a value smaller than 32. And 14 certainly fits the bill there. Okay. With the previous one, or the previous set where we're looking at elements, we were then able to go from moles to atoms. We're going to see something similar here. It's just in this case, we're thinking about molecules. So when we're using Avogadro's number, 1 mole of, in this case, saccharin, so C7H5NO3S. In this case, 1 mole of saccharin would be representing 6.022 times 10 to the 23rd molecules of this substance, whereas the previous examples were like number of atoms of gold. In this case, we're dealing with a molecule, so Avogadro's number is going to be related to the number of molecules there. But we're told that a packet of artificial sweetener contains 40 milligrams of saccharin. We've got the formula there. We've got the structure shown here. Given that saccharin has a molar mass of 183.18 grams per mole, so in this case, we don't have to go through and add up this formula to get that value. We're given it to us in the question. We want to figure out how many saccharin molecules are in that 40.0 milligram sample. And then specifically, we want to figure out how many carbon atoms are going to be in that sample. And with this one, the first one, going to be like very similar, like I said. We're starting with, oh, and actually in this case, I should point out, we had milligrams here, but the molar mass is in grams per mole. So we need to make those units cancel. We need to make them match up first. So we've got to convert 40.0 milligrams into grams. So we're going to divide by 1,000. We're going to get 0.0400, excuse me, grams of saccharin. And then we have the molar mass given to us, so we can match up the grams here. That'll give us moles of saccharin. And then just like with the atoms of gold, we can use Avogadro's number to then convert from moles of whatever that substance is into the actual number of molecules. So in this case, when we multiply by Avogadro's number, we're going to get 0.131 times 10 to the 20th molecules of saccharin. And again, that's a reasonable answer for this one because we've got a mass that's much, much smaller than the molar mass. So we should wind up with an answer that's several orders of magnitude smaller than Avogadro's number, 10 to the 20th versus 10 to the 23rd. That makes sense. So again, just always double check, make sure that your value kind of makes sense in terms of greater or smaller than 1 or greater or smaller than Avogadro's number, depending on the conversion itself, because we can always just use that as a quick way to double check that we're moving in the right direction. But then the second question, or the second piece of this question, wanted us to determine how many carbon atoms were present in the sample. So what we've got to do is go one step further. So we would actually set this up if this was the only question. We would set it up right from the beginning exactly the same. And then when we get to this point, we're in molecules of saccharin. But if we want to get to atoms of carbon, what we've got to do now is think about how a molecule of saccharin relates to carbon atoms. And what we can do is just use the chemical formula for that one, because with this next parenthesis, we need to cancel molecules of saccharin. So one molecule of saccharin will go on the bottom. And then based on this formula, we have 7 carbon atoms per molecule of saccharin. So we're just going to have that piece on top. So essentially, we're just taking our first answer, multiplying it by 7, since each of these molecules is going to contain 7 carbon atoms. And then what we see is our answer now, 9.17 times 10 to the 20th carbon atoms. And if we were looking at hydrogen, we would just have 5 hydrogen atoms on top, or 1 nitrogen, 3 oxygen, 1 sulfur, whatever it is for that particular element, just going to come from the chemical formula. So with the next one, how many C4H10 molecules are in a 9.213 gram sample? And how many hydrogen atoms? So C4H10 is just known as butane. So if you've ever seen one of like the Bic lighters, just going to have butane in it. So C4H10, just a organic substance, organic hydrocarbon. But just like this first one, if we want to figure out how many molecules of that substance we have based on this mass, we've got to use molar mass to get to moles first. Then we can use Avogadro's number. And the molar mass of butane, 4 carbons plus 10 hydrogens, going to be just over 58. So we can set it up so that grams cancel. And then to get to the molecules of butane, we've got to use Avogadro's number to cancel out moles. So for the first part, we could just stop after that second fraction. That would give us 9.545 times 10 to the 22nd molecules. And then for the second piece, to get the number of hydrogen atoms, each of these molecules contains 10 hydrogen atoms, so we're just going to multiply by 10. And that's why we see the order of magnitude just increase by 1. We're essentially just moving that decimal over one more spot to the right, making this value 1 order of magnitude larger. So we get 10 to the 23rd now, compared to 10 to the 22nd for the molecules. But we can still focus on these units to kind of help us go through these different steps. Because if we think about it, if we're given the mass of butane, the only possible thing we can do is then use the molar mass to convert to moles. So if we've got the formula, we've got a periodic table, we can always get the molar mass, even if it's not given to us in the question. So we can find that molar mass, convert to moles. And then thinking about just what a mole is, it's just a number. It's just Avogadro's number. So we can just multiply by 6.022 times 10 to the 23rd. And then since each of these molecules has 10 hydrogens, or if we were looking at carbon, we would just have 4 carbon atoms on top. But we can just relate the number of atoms per molecule using the chemical formula there. Okay, and then just a few more. So with this one, can't see because the Zoom thing's covering up. Okay, so determine the number of atoms and the mass of zirconium, silicon, and oxygen found in a 0.3384 mole sample of zircon. So you can see the formula there, which is a semi-precious stone. So with the number of atoms here, in this case, we're actually starting with moles already. So we can kind of skip a step. We actually don't need the molar mass for this question because we're already given moles. If we were given 0.3384 grams of zircon, then we would need the molar mass to convert to moles. But in this case, we can kind of skip that step since we're already in that unit. But for the number of atoms, we're again just going to use the mole in Avogadro's number. And then we'll use the chemical formula to figure out exactly how many zirconium or silicon or oxygen. So looking at all three of them, we're starting with that same zircon sample. So we're starting with the same number of moles. But then with this, 1 mole of zircon, think about it based on the formula, we'll have 1 mole of zirconium atom, or 1 mole of silicon atoms, or 4 moles of oxygen atoms. And again, it's just from the formula itself. And remember, mole is just a number, essentially. So if you get rid of mole there, if you want to think about it that way, 1 zircon molecule is going to have 1 zirconium atom, or 1 zircon molecule is going to have 1 silicon atom. 1 zircon molecule is going to have 4 oxygen atoms. So by putting mole in both of these spots, it's essentially just scaling up both of these the same, scaling them up by 6.022 times 10 to the 23rd. But it'd be the same thing as if we put dozen here. If we had 1 dozen zircon molecules, we'd have 1 dozen zirconium atoms. Or if we had 1 dozen zircon molecules, we'd have 4 dozen oxygen atoms, since each of those molecules gives us 4 oxygen. So once we get into the moles of those specific elements, now we can just again use Avogadro's number to convert to the actual number of atoms. And with zirconium and silicon, you're going to get the same answer, since we just have 1 of each of those in the chemical formula. But then with oxygen, since we have 4 oxygens per molecule, we get 4 times as many oxygens. So that's why we wind up with 8.152 times 10 to the 23rd. And then again, just focusing on sig figs, we had 4 sig figs in our initial value there. So we should have 4 sig figs in our final answer. And then with scientific notation, as long as we have proper notation, so the coefficient is something 1 between 1 and 9.9 repeating, any of the digits in that coefficient out in front are automatically significant. And then with the second piece, we're going to see in the second part of this chapter, with percent composition, there'd be a different way that we could approach this question. Probably still more difficult than what we see here, but we can actually start these exactly the same. So if you look for the previous half of this question, we started with moles of zircon and then just converted to moles of the atoms of those particular elements using the chemical formula. We're doing the same thing here. So now we're getting to moles of oxygen atoms or moles of silicon atoms, moles of zirconium atoms. But rather than using Avogadro's number to convert to the specific number of those atoms now, we're just using the molar mass to figure out how much each of those would weigh. So if we had 1 mole of zirconium atoms, 1 mole of zirconium has a molar mass of 91.224. So we're just multiplying by that, or 28.086 for silicon, just from the periodic table, 15.999 for oxygen. It's just, again, with oxygen, we've got 4 moles of those per mole of zirconium, or zircon, just because of the chemical formula here. Another way we could approach this is we use the moles here. We use the molar mass for zircon to figure out how many grams of this sample we would have. And then we could figure out the percent composition of this substance. Since it's a pure substance, it's always going to be the same amount of zirconium and silicon and oxygen relative to one another. So those percentages would always be the same. So we could then take the mass value that we determined. But again, I don't think that would be a simpler way to approach this, but we will start to see the percent composition in the next chapter, or the next section of this chapter. Oops, I meant to put, oops, I didn't mean to have the answer right away. So this one, to show the answer, because I guess I forgot to include the original question slide. But a tube of toothpaste contains 0.76 grams of sodium monofluorophosphate, so Na2PO3F. We want to determine the mass of fluorine atoms. And actually, I did not fully do that here. And one, I didn't spell grams correctly. But we've got the mass of that substance to begin with. So we can use the formula to get the molar mass, so almost 144. And we're going to cancel out grams, so we have 143.950 on the bottom. Gets us to moles of this substance, moles of the sodium monofluorophosphate. Then, using that chemical formula, 1 mole of sodium monofluorophosphate has 1 mole of fluorine atoms. And then 1 mole of fluorine atoms, using the periodic table, weighs just about 19 grams. So we can go through, cancel those units, we're only left with grams. But with this one, actually, we would want to go one step further, since it asks for, why is this giving me such a hard time? Since it's asking for milligrams, we really just go one step further. Equation, fraction, and 1 gram, oops, not 1 hectogram, 1 gram is equal to 1,000 milligrams. So we would just move this unit over. Is it 0.01? I forget what I had there. 0.76. I've already erased what I had, so I forget how many, if there was any zeros or not. 18.988 times 1,000. And we'll get a calculator answer of 100.302. But then if we think about this one, we've got 2 sig figs here. So we only want to have 2 sig figs in our final answer. So the only way to actually have 2 sig figs in this, because if we put 100 just by itself, that's only 1. If we put 100 point with the decimal there, that would be 3. So the only way to actually have this be 2 sig figs is to have it in scientific notation. So 1.0 means that both of those digits are significant. And then the 10 to the second gives us the correct number overall, so 100, with just that first 0 being significant there. And then with the second piece here, we want to figure out how many fluorine atoms were present in that sample. So again, we can start the same way. 0.76 grams divided by the molar mass gives us moles of that substance. But for every 1 mole of sodium monofluorophosphate, we get 1 mole of fluorine. And then we can just multiply by Avogadro's number to figure out exactly how many atoms that would be. And then again, 0.76, much less than 1 mole. So we should have much less than 1 mole of fluorine, since we're just multiplying by 1 here. And 3.2 times 10 to the 21st fits that. So we can be pretty confident in that answer, because we're winding up in the correct ballpark in terms of order of magnitude. But that will be the end of the first part of this chapter. And then the second one will start to look at similar types of questions, but of course with different angles to them.